Hello, Tim here. I wanted to do another wave speed equation example with an electromagnetic wave. So electromagnetic waves, if you see from the reading or the slides or my lectures over that, electromagnetic waves are waves like visible light, microwaves, radio waves, gamma rays, infrared, ultraviolet, all of that. Those waves all have in vacuum the same speed. They have different frequencies and wavelengths. And sometimes the numbers for these we can see. I'm going to link at some point in the class to some videos where you can see how microwaves can be used. If you use microwaves to melt chocolate in a couple of hot spots, you can measure the wavelength of microwaves and then use the frequency to find the speed of light. I'm going to do a quick math example here involving some radio waves. So that's my goal. I hope it's quick. Going to my board here, I have a reminder what the wave speed equation is. Wave speed equals frequency times wavelength, and I use the Greek letter lambda to represent wavelength. In vacuum, the speed of light is about 3 times 10 to the 8 meters per second. That's true to a couple of significant figures too, so I could write that 3.00 and it would be just as true. All right, so what is the wavelength of a typical radio wave? So, I don't know, I think with a lot of music going online and streaming being more popular, I get the feeling people listen to less radio than they used to, but one good source for news and podcast stuff, at least locally, is the NPR station. So I went to the link for that. You can see, right, there's their call letters and it's 91.5. And when you do FM, right, the 91.5 number means something. If you look on the one side, right, you can see that it's 91.5 megahertz. It's a different unit when you're talking about the numbers of AM stations. I believe those are written in hundreds of kilohertz, but I don't know. FM tends to be at least more popular and better reception in most places. So 91.5 megahertz is the frequency of the carrier. And I'm not going to go into radio a lot about the difference between FM and AM, but that's a good baseline frequency for the radio waves that are used in this case. So simple rearrangement here. What's the wavelength of this carrier? If I want to find the wavelength, what that is equal to the speed divided by the frequency. And the homework has a couple of questions we're going to practice doing exactly this. Deal is, right, the speed of all electromagnetic waves in vacuum is 3 times 10 to the 8th meters per second. Okay. You see the way I'm going to do this. Don't have a nice way to make a small one, but there's 3 times 10 to the 8th meters per second. And right, what we'll do is we'll divide that by the frequency, which is 91.5 megahertz. Now, that is the same as 9.15 times 10 to the 7th hertz. Seems, I think it's something like that, right? Mega, remember, means million, and million means times 10 to the 6th. So if I'm multiplying 91 by a million, that's the same as multiplying 9.1 by 10 million, right? So the wavelength is going to be, it's going to be the quotient of these two things. And as I've done, and I will do in other kinds of questions, you can see here, the divide by seconds and hertz, those are units that mean the same thing. Hertz are cycles per second, and on the top I have meters per second. So the per seconds, so to speak, the per seconds cancel out. We're going to be left with meters, which is a unit of length or wavelength. So the way that we finish this problem off is go to a calculator, and On the calculator, I use scientific notation, so 3 times 10 to the 8th. On Google Calculator, I used EXP. Your calculator has a EE or EXP button or something like that for scientific notation. So it goes like this. And then was it 9.15? I had E7, I believe, was the other one. And that gives me an answer there. It's just 3.28 meters about. All right. And back to the board again. The answer is this. It's equal to 3.28 meters. And that's going to be in the ballpark of about 11 feet. About 3 meters is roughly 10 feet. So yeah, when we say things like, you know, radio waves are relatively low frequency and relatively long wavelength, I mean, yeah, millions and millions of cycles per second sounds like a lot, but that's a really low frequency compared to other electromagnetic waves like visible light and infrared and ultraviolet and gamma and X-rays and so on. And the wavelength for radio is very, very long. Like wavelengths for things like visible light might be hair-sized, and for the higher frequency electromagnetic radiation, the waves may be the size of like a virus or a cell or something very, very small like that. We're not talking about 11 feet or things like this. So yeah, radio waves are considered a long wavelength version. And this won't be the last time we'll be using the wave speed equation, but I wanted to do it with electromagnetism. One thing in the homework that changes a little bit is that in a different medium, like a plastic or glass, the speed of light may be lower. It'll still be fast, but it won't be 3 times 10 to the 8th necessarily. You won't have to memorize any of those different numbers. I'll give them to you, but the methods of solving those problems is the same. So that's all for that example.